Hello everybody, and welcome to a video about section 5.2 about the definite integral. So you are watching this video because I was unable to get a substitute for class on Monday or Wednesday, but we can't afford to miss a full week's worth of material. So you will watch this video and read the section in lieu of class, and if I were you, I would do both those things as soon as possible so that you can get the homework finished by Thursday. So remember that the homework is now due on Thursday, which is the day before I get back. And so I will get back from my small little paternity leave on Friday, and on Friday we will pick up with section 5.3. Well, what is section 5.2 about? Recall what we did last time. So last time we defined left-hand sums and right-hand sums. Here's the definition of a right-hand sum. So remember how this worked. We had the graph of a function, and we wanted to approximate the area underneath that graph. So the area between this blue curve here and the x-axis. If you want to approximate that area, the easiest thing to do is just to use a bunch of rectangles. And so what you do is you chop your viewing window, which in this case you care about from A to B. You chop that window into n different pieces, if you're talking about n rectangles. So you chop it into n pieces, and each piece has the same length, so that these x1, x2, x3, all of those guys are equally spaced. So geometrically, that just means that your rectangles all have the same base length. So you have rectangles all the same length. Their heights, though, are different. The heights are given by the function itself. So if you want to figure out the height of this first rectangle inside of a right-hand sum, you use the right endpoint, travel up to the curve. That's how tall your rectangle is. Then your next rectangle. Start with the right-hand guy, go up. That's how tall your rectangle is, and so on. And you do this all the way. So you start here at x1, up, over, go all the way to b, which is xn, up, over. So this is the height of a rectangle. These are the base lengths of the rectangle. All the base lengths are the same. That's why we can use the same symbol for all of them. So you're doing height times base length, and then you're adding all those things up. So all that is doing is when I is 1, you're taking the area of this rectangle. When I is 2, area of this rectangle. I is 3, area of this rectangle, and so on. So the sigma is just a plus between all of those areas. And you could do the same thing with the left-hand sum. Notice you still have height times base length. All that changed from the previous formula was we used to start I at 1 and go up to n. So here with the first rectangle, we're starting with x1 to give us our height. x1 is the right-hand side. Then we truck our way all the way over, and b is xn. So having an n up here means we go all the way to b. Having an n minus 1 right here means we stop just one short of b. We stop right here. Because when we're doing a left-hand sum, we start at x0, which is a. So start at a, end at 1 less than b. If you're doing left-hand things, you never use the b, because b is not the left hand of anything. Okay, so we had left-hand sums, right-hand sums, and the idea that we ended class with last time was the following. If you use more and more rectangles, you will get a better and better approximation of the area that you want. And that area, again, is the area beneath this blue curve and above the x-axis. In particular, if you let that number of rectangles go to infinity via a limit for either one of these sums, you're going to get that area exactly. So these approximations by rectangles become arbitrarily good the more rectangles you have. So in particular, having more rectangles means you are shrinking their lengths to 0. So this delta x is actually shrinking itself down to 0. That's what this limit is doing here. Okay, so you get the actual area under the curve via a limit of left-hand sums or right-hand sums. So that's last time. We defined these sums, and we pointed out that these sums will give you an area if you take their limit. So what this section does is it just formalizes all of this and gives you a notation for dealing with this. So here's the notation that this section runs on, and what most of the rest of the course runs on. The definite integral of a function from one x value. Whoa, what happened? Why is it doing that to me? Okay, anyway, sorry about that. I don't know what happened. Anyway, the definite integral of f from a to b is given by this notation. So this s-looking thing is an integral symbol. A and b are your x values that are giving you your viewing window, if you like. So we're focusing our attention from x equals a to x equals b, the function itself, and then this dx. So in English you say the integral from a to b of f with respect to x. Okay, that's the English you use here. Integral from here to there of this particular function with respect to this independent variable. So x is the independent variable. So that definite integral is the limit of the left-hand sums, which also equals the limit of the right-hand sums, if those limits exist. So you can certainly create crazy enough functions so that those limits don't exist, but if those limits do exist, then say that f is integrable on AB, and the integral of f will exist. The numbers a and b themselves are called the limits of integration. The dx notation denotes that this integral is over, that the integral itself is over. So you can imagine writing a big string of stuff right here, and if you don't include that dx symbol, it's not clear where you're thinking of your integral as ending. So the dx avoids ambiguity, but also it tells you that the independent variable is x. And so I know that seems kind of stupid to have there, like, oh, independent variable is x. The independent variable is pretty much always x in a course like this. Although sometimes it's t, but you need that there because in higher level courses, particularly Calculus 3, if you make it there, you have multiple independent variables running around. So you need to be completely explicit about what variable this integral is happening with respect to. Also, notation-wise, when you write an integral down, you always have to have that there, or you will lose a point. It's proper notation for these two reasons here. Okay, so this section formally begins the study of integrals. So as I've told you numerous times, a Calculus 1 course runs on the concepts of derivatives and integrals. So here we go. We now have a definition of our second big concept. And notice an integral is a limit, okay? Just like a derivative was a limit. So on some level, this course is just about limits and nothing else. However, just like with derivatives, these limits are too hard for us to compute with the tools that we have in this course. So just like with derivatives, I will begin to give you shortcuts for evaluating these limits, thereby evaluating these integrals, and I'll start giving you those tools next time. But it is important to know that integrals and derivatives both are examples of limits. So both derivatives and integrals are the end result of some sort of infinite process, okay? N is going to infinity. If you could imagine n reaching infinity, you would get this integral. Okay, so let's begin our study of these integrals by talking about geometrically what they're giving you. And if you think back to derivatives, we started derivatives by thinking about the geometric interpretation of those. In that case, in the case of derivatives, the geometric interpretation was the slope of a tangent line. In the case of integrals, the geometric interpretation is an area. It's an area between the graph of f and the x-axis. In particular, if a is smaller than b, so you're thinking of moving from left to right here, like integral from 1 to 3, right? From 2 to 7, whatever. If a is less than b and f of x lives either on or above the x-axis, then the integral gives you exactly the area between the graph of f and the x-axis, and it gives you that area between x equals a, where you start, and x equals b, where you end. So back up here, If you integrate this guy, whatever this function is, who knows what that is, right? But if you integrate him from a to b, you're going to get the literal area here. Fill in everything under the curve. And of course, forget about the overestimates here, right? Forget about those. So take the shape formed by this blue curve, and then down to b, down to a. That filled in region, that's the integral from a to b of this function. Okay. If a is less than b, but f of x maybe doesn't necessarily live above the x-axis, then the integral gives you what's called the net area under the curve. So what's happening here is, suppose your function dips beneath the x-axis. In the definition here of like a left-hand sum, if your function is below the x-axis, that means that the function values are negative, right? Like if the graph at x equals 2 is under the x-axis, that means that f of 2 is negative. So if you're underneath the x-axis, you're getting negative terms in this sum. And of course, area is never negative. So what's happening is the integral now will be the area above the x-axis minus the area below the x-axis. So any area that's accruing beneath the x-axis, again, because the function itself is negative there, you're getting negative function outputs, you're going to have to subtract that area off. Okay, but that's the idea of an integral. So there's no like slopes of lines or anything here. An integral is basically just an area. If the function's above the x-axis, it's literally an area. The area that's trapped between the function's graph and the x-axis. If the function happens to dip below the x-axis, then again the integral you can think of as an area, but it's like net area. It's area above the x-axis minus area below. So here's our first example. Here's a picture of sine pi x. So it has a little sine wave going, right? And I've graphed it from 0 to 2. So if I ask you, hey, what's the integral from 0 to 2? What you have to do is take the area above the x-axis that's trapped between f and the x-axis. So you take all of this area here, the area of this like hill-looking thing, right? So who knows what that area is, right? I have no idea what this area is. I mean, I guess I do, but you guys don't, if you haven't had calculus before. But anyway, who knows what this area is? But at the very least, notice this area up here is the same as this area down there, right? This picture is symmetric. So if you just truck along from 0 to 2, you accrue your positive area, and then you accrue this negative area down here that matches what you just accrued positively. So the end result of that will be 0. The area above minus the area below is 0, because the area above is the same as the area below. So there you go. That integral there for that particular function, that integral is 0. Let's move on to a different example. So let's suppose f has this graph here. So sort of a jig-jagged sort of shape here. Let's think about several different integrals. First, let's think about the integral from 0 to 2 of f. What would that be? Well, let's go back up here. From 0 to 2, that means that on the x-axis, we're going from 0 to 2. Well, so this is where our attention is right now. Now we have to calculate the area under the curve. Well, the area under the curve forms this trapezoid shape, right? So I don't have the technology here to fill this in. I don't know how to do that, but just imagine this trapezoid filled in. That's the area between the curve itself and the x-axis. So that area, you got this rectangle here that's 1 by 2, it looks like. So you're going to get an area 2 right there. Then you got this triangle here that's base 2 and height 2. So 2 times 2 is 4, but then you got to cut that in half. I'll give you another 2. So those two shapes combined will give you an area of 4. So that is what that integral is. So when you're going from 0 to 2, the function lives above the x-axis. You don't have to worry about this negative area coming from beneath the x-axis. On the other hand, let's think about integral from 3 to 9 of the function. What would that be? So from 3 to 9. So now we're going from right here at 3 all the way over to 9. So now we have to think about the area between the curve and the x-axis from 3 to 9. So notice from 3 to 5, you have the area of a triangle. That triangle has base 2, height 3, so that's 2 times 3 is 6, but then you got to cut that in half. So from here to here, this whole chunk gives you a positive 3 area. But then notice you then go under the x-axis. So now you got to calculate the area of this sort of quadrilateral shape here that my mouse is tracing. You have to calculate the area of that now. So this isn't a particularly nice quadrilateral, but you can break it up into this triangle here that my mouse is tracing. So what's the area of this triangle here? Has base 2, height 3, so 6. Cut that in half is 3. But this area lives beneath the x-axis. So we're going to have to subtract that 3. So I had a positive 3 from here going. Now I have a negative 3 from here going. So far my total integral value is a positive 3 minus a 3 from down here. So 0 is what I got so far. Positive minus the area below gives me 0. So what's left is this sort of negative area here. So notice I have a square. I have a 2 by 2 square. So that's 4 area, but then negative 4 since it's beneath the x-axis. Then I have a triangle here of base 2 and height 1. So 2 times 1 is 2, right? And cut that in half is a 1. So then I have to subtract a 1 off of that. So here's my positive 3, then my negative 3 from that triangle, then my negative 4 from that square, and then, sorry, this is a typo. It should not be negative a half. It should be a minus 1. All right, so let's just confirm that. This triangle down here, right? Base 2, height 1, 2 times 1 is 2, cut that in half is 1. Okay, so sorry, this should be a negative 1 here for a final result of negative 5. That's your integral. Okay, so again, if somebody asks you like, hey, calculate the integral of this thing from here to here, if you have a graph going, you can just literally like compute areas as you go, remembering that the area above is positive, the area below counts negative. So you're going to take this area above minus this area below. So if you've really internalized that concept, you could have seen immediately that the integral from 3 to 9 should be negative. Right, because clearly there's more area beneath the curve than above the curve. So even if this function here were curvy, like the reason we could compute areas here was because everything was a straight line, right? So we just got rectangles and triangles. But even if this thing were curvy, I could still ask you like, hey, is the integral from 5 to 6, positive or negative? You would be able to answer that question simply by noticing, oh, from 5 to 6, it's all beneath, so negative. I could have asked you from the get-go, integral from, 0 to 7, right? Integral 0 to 7. Is that positive or negative? Well, clearly the answer is positive, because even though there is some negative area down here, it's outweighed by all of this positive area here. Okay, so you should be able to take a graph like this of straight lines and answer literal questions like this, but also comparison questions like, hey, is this positive or negative? Okay, so let's move on to a curvy graph. So at this point now, if I asked you hey, integral from 0 to 3, what is that? You would say, well, I don't know. First of all, I don't know the formula for this function anyway, right? Which back up here, I didn't really need to know the formula for f because I just had triangles and trapezoids and stuff, right? But anyway, so here, not only do I not have the formula for f, I also don't have triangles, trapezoids, rectangle. Because this curve literally is curvy now, right? The graph curves, it's not straight. So if I asked you integral from 0 to 3, you would tell me, well, without more data, I can't tell you that. I have no idea. But suppose I said to you integral from 0 to 3, positive, negative, or 0. Now you can answer that. Right? Because from 0 to 3, we're all underneath the x-axis, meaning a negative answer. So in any case, here's the question we will actually do. Let's list these integrals from smallest to biggest. So what you may want to do now is pause the video on this. So write these guys down, right? So you got these 5 integrals. Pause the video on this and see if you can actually list these things from smallest to biggest. So write these guys down. So maybe pause right now. I don't know. then pause here and see if you can list them from smallest to biggest. Okay, so assuming that if you paused, you have now unpaused. Let's talk through this. So I have 5 different integrals here, 2 to 4, 2 to 6. Let's start with those two guys. So 1, 2. 2 to 4 looks like it should be smaller than from 2 to 6. Right? So 2 to 6 spans this whole thing. 2 to 4 only spans this. So 2 to 4 looks like that answer is pretty close to 0. I have some negative area here and then maybe slightly more positive area there, right? So this positive area survives a little bit, but you take this chunk out of that. But if you go beyond 4 all the way to 6, all you're doing is accruing more positive area. So in other words, integral from 2 to 6 has to be bigger than integral from 2 to 4. Oops, all you've done is from 2 to 4, from 4 to 6, all you've done is just accrue all of this positive area. So at the very least, this guy right here is smaller than this guy right here. And they're both positive. Let's now think about integral from 3 to 7. What would that look like? 3 to 5, 6, 7. That's a lot of positive area, right? It's only positive. And it looks like it's bigger than anything we've seen so far, because like from 2 to 6, we had a bunch of positive area, but we had to take some out. We had to subtract this down here. But from 3 to 7, you're getting all that 2 to 6 area, but you're ignoring the negative stuff, and you're getting an extra little bit of area from going all the way over to 7. So from 3 to 7 looks like it's the biggest we've seen so far. Oh, and from 3 to 8, that must be even bigger, because from 3 to 8, that just goes this whole length of this positive area. So it looks like from 3 to 8 is the biggest possible area we could get no matter what. So suppose I just gave you this graph and said, hey, give me values a and b so that integral from a to b is as big as possible. All right, so let me repeat that. Suppose I said to you, give me x values a and b so that the integral from a to b of f is as big as possible. If you've really internalized this area concept, you would have been able to tell me 3 and 8. That's how you get the most positive area without paying any negative area cost. Okay, so all of that being said, here's the actual solution. From 0 to 2, right, you're just getting negative stuff. So clearly that negative stuff is smaller than all the other positive areas we had. So here's the correct ordering. 3 to 8 is the biggest, 3 to 7 second biggest, etc. 0 to 2 was the only negative answer, so it's clearly the smallest. Okay, so I want to end this video by talking about some integral properties. These are useful in your homework. The first property you should know is that you can switch a and b if you want to, but switching corresponds to like a perspective shift. So what used to be positive is now negative and vice versa. So when you make that switch, you pick up a negative sign. Okay, the integral from a number to itself, like from 1 to 1, right, of a given function, you should probably think about what that should be. But at the very least, if you're going from 1 to 1 and calculating the area, so let me come back up here. From 1 to 1, you don't move at all. You're just getting a line segment, I guess, is how you would interpret that. And then I'm asking you, what's the area of that line segment? But of course, line segments have no area. So you just get a 0 out of that. Okay, the next property, if you integrate a constant, what happens? Again, you should probably think about this and see if you can predict. But remember, if you graph a constant, all you get is a horizontal line. So if there's just a 3 in here, right, f of x equals 3, that's just a horizontal line at 3. So this integral in that case would be representing the area of a rectangle. It's a rectangle that stretches from A to B, and the height of that rectangle is C. So there's what that looks like. Height C, and if the length runs the whole gamut from A to B, the distance from A to B is B minus A. So here, if you had like from 1 to 3 of 7, what you're saying is, oh, my rectangle starts at 1, ends at 3, and 3 minus 1 is 2. That's your base length. And if you have a 7 right here, you're just saying that rectangle has height 7. So you would have 7 times 2 right here. You can guess what happens here. Probably just like with any limit, you can split things over pluses and minuses. So the integral of a sum is the sum of the integrals. Same for a difference. Just like with any other limit, you can pull constants out of the limit if you want to. So that was true of derivatives. It's still true here. So here's an example using these properties. Given this piece of data, so I'll just tell you that, let's find this, integral from 4 to 0 of all this stuff. Notice, got my dx at the end, right? Dx is everywhere. That's proper notation. Okay. So here's the whole thing written out. From 4 to 0, that's kind of obnoxious. Let me write it from 0 to 4. So I'm thinking from left to right now. Making that change cost me a negative sign, but that's all right. So now what I do is I take this integral here and this integral in here and split it over the differences and sums. So I use property, 4 here. So that's how I get to this line. So I can do integral of 2 minus integral of x, plus. And notice I already pulled the 5 out. So I'm allowed to do that by rule 3. You can pull a constant, rule 5. You can pull a constant out of an integral. Okay, so from here to here was rule 3 right there, and rule 4 that says you can split integrals over sums and differences. And now the integral from 0 to 4 of 2. Well, rule 3, all you got to do is integral 0 to 4 of 2. You get a 2 right here, get a 4 minus 0 there. 2 times 4 is 8. There's that 8. Minus integral 0 to 4 of x. So currently, I haven't told you a way to deal with this explicitly, but if you think back to this example here, wherever it is, if you have a graph, and that graph is made up of straight lines, then any integral is just going to be the area of a trapezoid, a triangle, a rectangle, whatever, So if your function consists only of straight lines, you can always figure out the integral directly by just graphing the thing and using geometry. So back here, what does the graph of x look like? The graph of y equals x is a straight line. So any integral of that you can figure out by just looking at the corresponding triangles. And if you do that, you will get an area of 8. So I will leave that to you to verify, but simply draw the graph of y equals x, look at the triangle formed from x equals 0 to x equals 4, and you'll see you get something of size 8. And then here, this integral was directly given to you, 64/3. So I now have 5 times that. So 8 minus 8 is 0, right? So all I'm left with is this 5 64/3, and I had this negative out front from the very beginning. So here you go. Here's an example of something you might see in your homework that uses those properties. Okay, let me just close with 3 more properties here. The integral from a to b plus the integral from b to c. You can probably guess what that is. This is just saying take the area from a to b and then take the area from b to c. The end result will be the area from a to c. Also, if f is never negative, so it's either on the x-axis or above, then of course the integral is positive or 0. Because all you're doing is accruing positive area if you never dip below the x-axis. So this condition is saying you never dip below the x-axis, so you never get any negative area. Also, if f is bigger than g, that just simply means the graph of f is above the graph of g. That will mean that f's area will be bigger than g's area. Okay, so finally, let me just close by saying, in the homework, you might be asked to evaluate something like this. And if you think about it, after watching this video, you have basically just 2 tools to do something like this. You can try to think through the integral properties that I just listed, or you could think about the geometry of the situation. So just like, go all the way back right here. Geometry of a situation, right? Calculating areas directly because the areas are nice. So we go all the way back here. Okay, so the integral properties we have aren't terribly helpful here. There's an absolute value, But the geometry is immediately useful if you just know what the absolute value function looks like, and it looks like that. All right, so the absolute value function itself just consists of straight lines. So any integral of this guy is just going to be triangular areas, okay? And maybe rectangular ones. Like if I go from -3 to 2, I get this rectangle here plus a triangle up top. But in any case, if you see an absolute value in your homework or something like that, just use the geometry of the dude's graph. So just draw this guy's graph. So we're going from -2 to 4, right? So -2 to 4. Notice I just get this this triangle here, and then I'll get a triangle there also. So just add the areas of the two triangles. Okay, so at the end of this video, you are now able to basically do two things, and they are listed right here. Basically, I can give you a graph and ask you, just from the geometry, to analyze certain integrals. So maybe I ask you to compute them directly, like we did here. With this example, we literally computed things. Or I could give you a graph and just ask you sort of general things, like, hey, what's the smallest, what's the biggest, right? So you should be able to use geometry to say things about integrals. And secondly, you should be able to do questions like this. So somehow using those integral properties that I listed for you. Okay, so that's all for this section, and we will pick things back up in section 5.3. In 5.3, we will completely short circuit this limit definition, so wherever it was here. So right now, again, the only tools you have are basically geometry, right, to calculate integrals. So in section 5.3, I will give you this like big hammer theorem that will completely short circuit the geometry and short circuit these limits. It will just allow you to immediately calculate all sorts of integrals. Okay, and I'll see you on Friday.